Alright, hello everyone. These are the introduction slides to our second lab for the course, which is on phosphate absorption onto iron-coated sand. So again, this lab is dealing with adsorption, so we'll just start with some quick definitions. So adsorption is a process that occurs when a gas or liquid accumulates on the surface of a solid or a liquid, which is known as the adsorbent, forming a molecular or atomic film, which would be the adsorbate. Absorption, on the other hand, is a process in which a substance diffuses into a liquid or solid to form a solution. Sorption can then also be used to describe the combination of adsorption and absorption processes, or when you just don't know which one's happening. So from the figure down here, you can see that absorption, the adsorbate is diffusing into the adsorbent, whereas for adsorption, which is what we're going to be dealing with today, we have the adsorbates kind of binding onto the adsorbent. So these two words will be used a lot today, adsorbent and adsorbate, so just kind of know the difference between the two. So adsorption of gases and solutes is described through something called isotherms. So an isotherm describes the amount of adsorbate on the adsorbent as a function of pressure for gases, or as concentrations for liquids at a constant temperature. The quantity absorbed is a function of the mass of the adsorbent and the volume of the adsorbate. So this is an example of an adsorption isotherm for copper absorption onto some sort of tea leaves. And they did this experiment at different temperatures. So we'll kind of be doing something similar today. The only difference is we're going to be testing different masses of our adsorbent rather than different temperatures. So what they did for this experiment is they took a fixed mass of their tea leaves, their absorbent, and they added varying concentrations of a copper solution. So as you can see, they had their different concentrations steadily increasing from I think about 0.6 to about 14 milligrams per liter of their copper. So on the x-axis here we have what is CE, which is the concentration equilibrium, or the final concentration of the solution. And on the y-axis we have Q, or QE sometimes, it's described as, which is the absorption at equilibrium. So QE is represented through this equation here, which just incorporates the initial and the final concentration of your absorbate, in this case that was copper, times the volume of your solution that you used, and also divided by the mass of your absorbent. So we'll be looking at two different isotherms today. The Langmuir is the first one we're looking at. So the Langmuir isotherm assumes a uniform surface with monolayer adsorption. The adsorbed and desorbed molecules also are assumed to exist in equilibrium, and they exhibit the ideal gas behavior. So the Langmuir isotherm is described by this equation here, and this is the linearized version of it. So we have 1 over QE, and that is our y term when we're actually going to be plotting this. And we have 1 over CE as our x term. So a disadvantage of using this Langmuir model is that it doesn't account for any heterogeneities. So basically where there can be different types or many different types of binding sites, it just kind of assumes a uniform surface. So now we have something from the absorption isotherm, and we're plotting our Langmuir isotherm that looks like this. So we have a linearized version of our equation up at the top. And this is what one of these adsorption curves would look like when you're just taking the inverse of QE and of CE and plotting it out. So up in this equation, we have our 1 over QE, which is again our y term. We have 1 over Q, which would be our intercept. 1 over C is our x term, and 1 over BQ is just the value in front of the x. So as for the variables B and Q, Q is the monolayer absorption capacity, while B is a constant related to the free energy of adsorption. Kinetic experiments would go much further into detail about these parameters, but for our lab we are just focusing on QE, the equilibrium concentration of the absorbent, and CE, the equilibrium concentration of the absorbent, and QE, which is the amount of absorbent absorbed onto the absorbent as a function of mass of the absorbent and the volume of the adsorbate. So the other type of isotherm we'll be looking at today is the Freundlich. And the Freundlich isotherm is used to describe multi-site absorption for heterogeneous surfaces, so it does take into account that there could be many different types of binding sites. So this relationship is described by the equation just down here, and pretty much you're just taking the log of QE and plotting it against the log of CE. So now from again one of these absorption isotherm curves, once we take the log of each axis, we'll get a nice linear equation that looks just like this. So again, we have our log QE, which is our y term, our log CE, which is our x, 1 over n, which is this variable in front, and log kf is the intercept. So as for the variables n and k in this equation, as the temperature increases, kf and n will change to reflect the empirical observation that the quantity absorbed, or the QE, rises more slowly and higher concentrations are required to completely saturate the surface. So for anybody who was in lab today, we will again be creating our own absorption experiment with phosphate as our absorbate and iron-coated sand as our absorbent. So for the in-person labs, all the work will have been divided among the 4 lab sections, with 2 of the sections testing 1 gram of iron-coated sand with phosphate solutions, and the other 2 sections testing 2 grams of iron-coated sand with their different phosphate solutions. So again, we're creating our absorption isotherms and testing the amount of the absorbent, which is our iron-coated sand, and how that kind of affects the absorption. So for each absorption isotherm, there will be 6 different phosphate solutions made of different concentrations. So each section will prepare 3 of these concentrations to make up 6 for the 1 gram, and then the other 2 sections each will make 3 concentrations with their 2 grams of iron-coated sand. Once the phosphate standards have all been made, the sand will be added to each and will be stirred for 2 hours. So that was just the first part of the lab. Then we can kind of actually get into what iron-coated sand actually is. So again, phosphorus is often present in low concentrations in water and wastewater. It's a key limiting nutrient for the growth of algae and other microorganisms, which in excess can cause eutrophication of these water bodies. So there are some methods that have been developed for phosphorus removal, such as chemical precipitation with aluminum, iron, and calcium salts, biological processes that rely on biomass growth and absorption, and absorption as the last process. So among these methods, absorption is highly effective, it's also economical, and has low sludge production in wastewater treatment plants. Most importantly though, it is an excellent removal strategy for low concentrations of phosphorus. So lots of studies have shown that metal oxides, such as iron or aluminum oxides, have a relatively high surface area and surface charge, and these could be applied to the removal of heavy metals and organic matters from wastewater. So most of these metal oxides are only available as a fine powder though, So they are limited to large reactor configurations, and due to their low conductivity, the metal oxides alone aren't really suitable as a filter material. In past years, though, some researchers have developed techniques for coating these metal oxides onto a sand surface in order to overcome these mentioned problems of just using these metal oxide powders by themselves. So the sand, as seen in the picture right here, was coated by adding a ferric nitrate solution to some clean sand. It then turned this kind of reddish-orange color as the ferric oxides precipitated out. And there's just more details about that process in the lab write-up. So again, phosphate absorbs strongly onto these ferric oxides, and it is a really quick reaction between the phosphate and the iron-coated sand, with over 90% of the uptake occurring within the first 2 hours of contact. But there are many other factors that can influence the uptake efficiency. So today, again, we'll just be investigating the effect of the amount of the absorbent on the uptake of phosphate. But there are other parameters such as temperature. pH is a really big one, contact time of the phosphate with the sand, interfering species, so competitive ions, and the particle size of the absorbent, which can influence the uptake. So when we actually move into our modeling lab using modeling software such as FreakC, we can actually use the models or the modeling software to test out these different parameters that we won't really have time to show in the lab. So to see how something like pH, different pHs would affect the uptake of the phosphate onto the iron-coated sand. So if you're attending the lab this week or attended it in the last 2 weeks in person, the other half of this lab will include making your own standard curve, just using the same concentrations and dilutions as for the previous lab. And then from the standard curve that's been made, everybody in the class will be able to test out the unknown that they brought in. They'll be able to determine the initial concentration of their phosphate solutions that they'll be making, and they'll also be able to test the final phosphate solution concentrations to see how much phosphate has been taken up by the iron-coated sand. So that's just the introduction for this lab, and if you're unable to attend the lab in person, I'll just now be showing a demonstration of what we actually did in this lab. Alright, hello everyone. This will be a video demonstration of Lab 2. So as you guys just saw in the slides, we're doing an absorption experiment today, where we will be varying the mass of our absorbent, which is our iron-coated sand. And I have a little flask of it right here, using different phosphate solutions with the sand. So I just want to mention that all of the data collected in this video will not be used in the assignment. This is all just for demonstration purposes. All of the data that will be needed to complete the assignment will be uploaded onto Learn, and the whole class will use the same data set. So whatever numbers I get for today, just ignore them as they are just for demonstration purposes. So as you guys saw in the assignment online, we're making a bunch of standards today of phosphate that range from 15 to 1 milligram per liter. All of the standards will be made from a 15 milligram per liter standard, as I have here for this demonstration, and I will just be showing you how to make the 1 milligram per liter standard of phosphate. For this demonstration, I will just be using phosphate standards of 1, 2, 5, and 10 milligrams per liter. Alright, so I'll start making our 1 milligram per liter phosphate standard using our 15 milligram per liter phosphate standard to do this. So if you guys saw on the assignment on the Learn website, there is a table that displays all of these standards and their starting concentrations and how I actually diluted down to the 15 milligram per liter standard that I'm using in this video. So again, in that table, for the groups that are in person for the labs, they are making standard solutions that range between 0.5 to 15 milligrams per liter of phosphate. So they will be making 6 standards for the lab. Again, for this demonstration, I will only be making 4 standards, and I'll be making the 1, 2, 5, and 10 milligram per liter phosphate standard. The only standard I'll be showing how to make is the 1 milligram per liter standard here on camera, as the rest have already been made. So to make the 1 milligram per liter phosphate solution, we will be adding 56 milliliters of pure water and 4 mils of our 15 milligram per liter standard. Normally, to measure out 56 milliliters of water, we would use a scale to be a little bit more accurate, but since we don't have those materials for everybody in the lab, I'll just be using this 25 milliliter graduated cylinder. So now that I've added the 56 mils of water into our 1 milligram per liter bottle, I can add 4 mils of the 50 milligram per liter standard. So before we get started on making our absorption isotherm, we just want to verify the initial concentration of the solution we made. So for the people that will be attending the in-person labs, they will be making their own standard curve again, the same way from Lab 1 to analyze their phosphate samples. For this demonstration, we will just be directly measuring the concentration of our phosphate solutions. So this spectrometer is from the company Hack, and while they can measure absorbances for standard curves, they can also just directly measure the concentration of compounds. So to do this for phosphate, I'll be using something called the powder pill ascorbic acid method for phosphate analysis. So if we just go into favorite programs here, there is one for reactive phosphate, and it does say 2.5 milligrams per liter on the side. So that just means that is the upper range for this method, and the actual range is about 0.02 to 2.5 milligrams per liter as phosphate. So we'll just hit start on here, and as you can see, our units are already in milligrams per liter as phosphate, which is good because that is the units that we want. So this technique uses 20 mils of our sample. So we'll put 10 mils into one cuvette and 10 mils into the other using the 5 mil Eppendorf pipette. So now that we have added 10 mils of sample into each cuvette, we will be taking one of these powder pillows here, which is just our reagent. So this method essentially uses the same principles as for the standard curve we made in the last lab with our liquid reagent. The ascorbic acid is still the main active ingredient in the reagent, as it reduces the phosphate. So how this technique works is just we add our powder reagent into one of our cuvettes, and in our other cuvette is just plain sample, which will act as the blank. So we will just open this pack up, and usually you do this in the fume hood to avoid getting the powder everywhere, and always make sure to wear safety goggles when using these packets. So we'll just add the whole packet into one of these cuvettes. We'll add a piece of parafilm on top and give it a good shake for 20 to 30 seconds. So this method is available online. If anyone is interested to read through the whole method, you can just look up orthophosphate reactive hack, and it should show up as a PDF. So we will just give this a good shake for about 30 seconds. So this method does have a 2-minute reaction time after you shake it, and you can just press the little timer symbol on the hack to start this. So our time is almost up for the 2-minute reaction, and again we are just doing this part to verify that the 1 milligram per liter phosphate solution we made is actually 1 milligram per liter. This is always good to do for any solution that you're making, just to double check that you've made the right concentration. So again we have our blank, which is just 10 mils of our sample with no reagent in it. And as always, give your cuvette a good wipe down with a chem wipe and place it inside the spectrophotometer. Then close it and press 0. So for this method, each new solution that you're analyzing has its own blank, and the blank will always just be 10 mils of your sample with no reagent added. Now that our blank is done, we can put our sample in, and it is a bit blue. I hope you guys can see that, it's just not my gloves. So again, this method can only do up to 2.5 milligrams per liter of phosphate. So if we were doing, let's say, our 10 milligram per liter standard, we would have to dilute it down about 10 times for it to fall within the range. So I'll just press read for the sample, and we're getting a reading of about 1.03 milligrams per liter of phosphate. So now that we've verified our initial concentration for our 1 milligram per liter solution of phosphate, we can move on to the absorption isotherm. So now that we have the initial concentrations of all of our standards, I just did the other 3 off camera, we can actually start the absorption of the phosphate onto the iron-coated sand. So we will just take our remaining standard, which is about 50 mils, and we will be adding it into this 50 ml centrifuge tube. I'll also be adding in our 1 gram of iron-coated sand, which is the mass I'll be using for this demonstration. Again, for the lab, there will be 2 masses of iron-coated sand tested, one at 1 milligram and one at 2 grams of sand. So there is 1 gram of iron-coated sand pre-weighed that I've just poured into the centrifuge tube with the rest of our 1 milligram per liter standard. So this is actually the rotator here, and what you do is you just take your centrifuge tube, clip it into one of these clips right here, and just turn it on, and it just mixes on its own. So again, I'll just leave these for 24 hours to mix, and I'll come back and finish this tomorrow. So it is now the next day, and I realize I forgot to show you guys the rest of the centrifuge tubes that the other 3 standards were made in. So again, this is our 1 milligram per liter solution with our 1 gram of iron-coated sand. We also have a 2 milligram per liter, a 5 milligram per liter, and a 10 milligram per liter phosphate solutions, all with 1 gram of that iron-coated sand. So these have taken on a little bit of a reddish-orange hue after being in the rotator for 24 hours. Now that these phosphate solutions have been left to adsorb onto the iron-coated sand for the 24 hours, we can analyze the final concentration of each of these solutions to see how much phosphate was adsorbed onto the sand. So I'm just going to speed through these analyses again, and we'll just go ahead and choose the same program on the spectrophotometer for the 2.5 milligram per liter phosphate method, and we'll start with our 1 milligram per liter standard. So again, I'm just adding 10 mils of each sample, or of the sample, into each cuvette. And none of these have any dilutions needed, as they'll all fall within the 2.5 milligram per liter phosphate range. So I'm just adding the phosphate reagent, one of those powder pillows, into one of the cuvettes, giving it a good shake, and we'll be waiting the 2-minute reaction period. So now the 2-minute reaction is pretty much over, and again I'm just analyzing for the final concentration of the 1 milligram per liter standard. The blank is already inside, so we'll just go ahead and 0 for that. Again, no dilution was used for the sample, and the blank is just 10 mils of the sample with no reagent added. So again, we'll give our cuvette a wipe down with a chem wipe, place it inside, and just press read. So we're actually getting a negative concentration for this standard, and this is just likely due to there being 0 phosphate left in the solution. So that just means that the sand was able to absorb all of the phosphate from the solution. So So this final concentration of the 1 milligram per liter solution is effectively 0. So next we'll just move on to analyzing the final concentration of our 2 milligram per liter phosphate solution with our 1 gram of iron-coated sand. We have the sand in the bottom there, which you can see was a little bit reddish brown. So again, no dilution needed for the sample as the initial concentration was already below the upper bound of this method. So I'll give these cuvettes a quick dry, and again I'll add 10 milliliters of sample into each one, and just repeat the process with the powder pillow and waiting the 2-minute reaction period. Alright, so it's been 2 minutes. I will put our blank in the spectrophotometer, which again is just 10 mils of sample with no reagent. We will zero that, and then we'll put our standard in. So for our 2 milligram per liter initial phosphate solution, we have a final concentration of about 0.04 milligrams per liter. So finally, we will do our 10 milligram per liter phosphate solution with our 1 gram of iron-coated sand to determine the final concentration. I forgot to show the 5 milligram per liter solution on camera. I thought it was recording, but apparently it wasn't. But I'll show the results from that in the next clip with all the data. So again, we're just doing the same method of just adding the 10 mils of sample to each cuvette, added the reagent into one of them, and waited the 2-minute reaction time. So there's no dilution on this sample either for the final concentration, so we'll just put our blank in and press 0. So for our 10 milligram per liter standard phosphate, we're getting a final concentration of 0.9 milligrams per liter of phosphate. So now I'm just going to organize all this data in Excel, and I'll do a quick tutorial on the calculations you'll be doing in this assignment. Alright, so now that we have all of our data collected, we can now actually make our absorption isotherms, and I'll just be using Excel for this example. So these were the 4 concentrations I worked with for this experiment. I did a 1, 2, 5, and 10 milligram per liter phosphate solution. And these were the initial concentrations measured by the spectrophotometer. So I did this one on camera. This is the one we had for our 1 milligram per liter phosphate solution. It ended up being 1.03 milligrams per liter, the actual concentration. And these other 3 I just did off camera. So again, for the first 2 standards, there is no need to dilute any of them, as this method has an upper range of 2.5 milligrams per liter of phosphate. But for the 5 and 10, they did have to be diluted down a bit. So I did a 10 times dilution so that it would fall within the range of about 0 to 2.5 milligrams per liter of phosphate, and these are the numbers I had. But now we can take our corrected values. These ones don't need to be corrected at all since there was no dilution. And these just simply have a 10 times dilution, so this will just be this times our dilution. So these were all of the actual concentrations. Now for our final concentration, this is what we did in the video. For the first one we got a value of 1. For the second one we had a value of 0.6. For 5, forgot to show that one on camera, but we had a value of 0.15 or 0.15. And for the 10 we had a value of 0.9. So there was no dilution for any of these as well, as they would all fall within the 2.5 range. So no need to correct any of these values, and we can just copy them over. Alright, so now we can use this equation here, as mentioned in the slides, to actually build our absorption isotherm. So we have QE, which will be on our y-axis, and all the parameters we'll need for that. And then CE, which would be our final concentration, would be on the X. So for these we will need our V, which is our volume of solution, which is our adsorbate. We also have M, which is our adsorbent. So for our V, our absorbate, we used 50 mils of solution. So that's 0.05 liters. And for our mass, we use 1 gram of iron-coated sand. So our QE is just our initial minus our final times the volume of your absorbate. Make sure you put your $sign in to keep this a constant, divided by the value of our absorbent. Oh, shoot. There we go. So if you guys notice, I did change this CE value from 0 to 0.02. That's only because this will introduce some problems when we try to do our Langmuir and our Freundlich isotherms. You can't divide by 0, and you also can't take the log of 0. So pretty much, if you guys look back in the video, we did get a negative absorbance for this. This was likely just under the measuring range. I believe the measuring range for the spectrophotometer for that phosphate method was 0.02 to 2.5 milligrams per liter, so it was likely just below 0.02, but we'll just use 0.02 as the value for this, just to put it right at the lower bound there. So now that we have our X, our CE, and our Y, we can graph this out. And here is our absorption isotherm. So if we did increase our initial concentrations, this would likely just plateau eventually. You'll see that in the assignment data that you get. But for now, it would still be increasing, which means the sand still had room to absorb more phosphate onto it. So this is what you're building for your absorption isotherm. Just make sure to label your axes as QE and CE on the bottom, give it a nice title. And now we can move on to Langmuir. So to build the Langmuir isotherm, we simply have 1 over CE as our X and 1 over QE as our Y. So we'll just do equals 1 over CE. Drag this down. And 1 over Q. Okay, so here's our Langmuir isotherm that we have. We have 1 over CE on the X and 1 over QE on the Y. So if we insert a trend line for this and show our equation of the line and the intercept, what we get for that. So we get a 0.99 r squared value, so the relationship looks pretty good. Now we can move on to the Freundlich. We have to take log of CE and log of QE. So just equals log CE, drag it down, and log of QE. Insert another chart for this. I'll add a trend line to see the relationship. Alright, so we got 0.96 for the Freundlich isotherm. So just for this lab, the r squared value, you guys can just say that that the Langmuir model would fit this better, just based on the r squared value, as opposed to the Freundlich. In reality, a lot more things influence this relationship between mass of your absorbent and your volume of your absorbate. But I won't get too much into detail about that in this lab, but if you guys want to read up on it more, there's plenty online about how these relationships are influenced, and what the Langmuir and Freundlich isotherms actually represent. So that's all you'll be doing for the lab today. Again, do not use any of this data that I collected. I'll be posting all of the data on Learn in one big Excel sheet, and it'll look something like this table here that you guys will get. So you'll just have to build your absorption isotherm, and then also make your Langmuir and your Freundlich isotherms from there.